Hello everyone, this is lesson D3 on derivatives of polynomials and exponential functions. So in lesson D2 we learned that the derivative f prime of x is the limit as h goes to 0 of f of x plus h minus f of x over h. And to find the derivative of, for example, x squared, we had to do this process and then we got out an answer of 2x. Now, it turns out that the people who invented calculus noticed certain patterns for how the answer to a derivative problem always comes out. And so using that, they created certain rules that we can use when we're finding derivatives. So we're going to be able to now find our derivatives. Now that we know that what a derivative is this is what we're doing. Now that we know that, we can shortcut the process and learn how to find derivatives of, in this case, polynomials and exponentials without going through the whole process. So let's first begin with these functions that are constant. So f of x equals 5, that just means y equals 5. It's a flat line. The slope of that line is 0, and so the derivative here, f prime in the second column, would be equal to 0. It's the function f prime is equal to 0. If you have a flat line at y is equal to -1, the derivative is 0. If the line is at y is equal to pi, it doesn't matter. The derivative is still 0. So these are functions, right? F prime of x, f prime of x, f prime of x. We can evaluate the function f prime at any x value. So if I said f prime of 1, then for this case, when you have a flat line, to start with, f prime of 1 is going to be equal to 0 for all of these three examples. Because you put 1 into this f prime equation, but the f prime equation doesn't depend even on x. The answer is always going to be 0. So what we're saying is that the slope of these lines right here is always equal to 0. Okay, let's talk about straight lines. For straight lines, the derivative is the slope of the line. So if f of x equals x, then the derivative is equal to 1. If f of x equals -x, the slope of that line is -1, so the derivative is equal to -1. If you have a function that instead of f of x, we say s of t, this is typically a position function, and t is the time variable, we have to realize s of t is a straight line, 2t, so f prime of t is equal to 2. Now, these are also functions where no matter what x value you put into the derivative function, you just get out the same answer, right? So I could put in 1 or -1 or whatever I wanted to these functions as x or as t, and I would just get out the same answer. Is equal to 2 in this case. I guess I should say 1 here because at the top I said that this column, this third column right here, is always just going to be the derivative f prime of the derivative evaluated at 1. Okay, so then if you take the power rule, this is a big deal because people who did this limit process on the power functions noticed a certain pattern, and by power functions I mean like any x with an exponent, right? So people did this whole limit process on these functions, and they realized a pattern, and the pattern is that the derivative always ends up being, you bring this exponent down out front, and then you reduce the exponent by 1. So 3 minus 1 is 2. So if f is equal to x cubed, f prime is equal to 3x squared. It works out the same way for the quadratic. We did it with the limit method, but if you look at it from this rule, then f prime for x squared, you bring the 2 out front, there it is, and then you subtract 1 from the exponent, and so we have 2x to the 1, or 2x. X to the 4, the derivative is bring the exponent out front and reduce the exponent by 1, so 4x cubed. Okay, so I think I have the same examples over here. f prime of x is 2x for x squared and 3x squared for x cubed. S of t is equal to t to the 5. S prime of t would be 5 t to the 4th. S of t is equal to t to the 100. S prime of t will be 100 t to the 99. So that's very simple and very useful. Now I'm gonna put in 1 when it says here f prime of 1 in this last column, right? That means we're evaluating the derivative at x is equal to 1. We're putting 1 into the x value of the derivative equation. So f prime of 1 for each of these would be 2 and 3 and 5 and 100, because 1 to the power 99 is 1. Okay, when you have a negative power, the power rule still works, but you need to be a little careful. So if f of x is x to the negative 1, f prime of x is, bring this down, negative 1, and then reduce the power by 1 means it's going to be x to the negative 2. So this is negative x to the negative 2, which we can rewrite as negative 1 over x squared. If v of t is t to the negative 5, v prime of t is negative 5, that's bringing the power down, t to the negative 6, and that can be written as negative 5 over t to the 6. If f of x is x to the negative 100, pause the video and see if you can get that. F prime of x will be negative 100, x to the negative 101. And that written as a positive exponent would look like negative 100 divided by x to the positive 101. So these derivatives, when you have a negative power to start with, you can see that all of the derivatives cannot be evaluated at 0, right? So we're noticing that. We're not going to be able to find f prime of 0, but we can do f prime of 1 for each of these and get a number out. And again, that's just reminding you that f prime of 1 means you just take 1 and put it into the f prime equation. If you were doing, for example, f prime of negative 1, you take negative 1 and put it into the f prime equation. So f prime of negative 1 for these three would be negative 1 over negative 1, the quantity squared. The first one would be negative 1. The second one would be negative 5 over negative 1 to the power 6, which would be negative 5. And the third one would be negative 100 over negative 1 to the 101 power, which is negative 100 over negative 1 or positive 100, okay? Okay, fractional powers, the power rule also still works. So f prime of x, bring down the power, 1/3. Let's move this over a little bit. Okay, so it's equal to 1/3, and then subtract 1 from the exponent. So 1/3 minus 1, that's equal to 1/3 minus 3 over 3, that's negative 2/3. So x to the negative 2/3, and if you wrote that as a positive exponent, it would be 1 over 3 x to the 2/3. This guy, rad x, you know how to take that derivative, but you have to recognize it as a power, x to the 1/2. Then f prime of x is 1/2, x to the 1/2 minus 1 or negative 1/2. And so bring the power down for a positive exponent like that. This guy, you have to know from pre-calc or algebra 2 that this is the same as a to the 2/5. So then g prime of a, notice, use the function name and the variable name that you've been given, be consistent with that. So g prime of a is 2/5 a to the 2/5 minus 1, that's 2/5 minus 5/5, which is negative 3/5. So a to the negative 3/5, and then I have, this is equal to 2 over 5a to the 3/5, okay? So, and then you can practice putting in different numbers into these. If you put in 1, for example, in the first one, you get 1/3. And you can practice putting in different numbers into those equations to evaluate the derivative at any place. Let's take a look at tangent line and normal line equations. Find the equation of the tangent line and the normal line to the graph of f of x equals x rad x at the point 1, 1. To write the equation of a tangent line, you need a point, you need a slope. The point, they already gave it to you, it's 1, 1. The slope, we're on this graph, f of x is equal to x rad x. We need the slope, which is f prime of x, and we need the slope at this particular x value here that we're at. So we need the slope f prime of 1. Okay, so f prime of x, you're going to get by the power rule. You have to recognize that this can be written as x to the 1 times x to the 1/2, which is x to the 1 plus 1/2, which is 3/2. And now you do the power rule. Bring this power down, 3/2, x to the 3/2 minus 1, which is, let's check that out, 3/2 minus 2/2, or 1, is equal to 1/2, right? So be careful with the fractional exponents to get it all right. 3/2 x to the 1/2, when you put in 1 into that, you get 3/2. So the slope of this graph at x is equal to 1 is 3/2. And now I'm ready to write the tangent line equation. Y minus y1 is equal to m times the quantity x minus x1. This right here is your x1, y1, and this right here is your m. So I can write y minus 1 is equal to 3/2 times the quantity x minus 1. Reminder of two things. One is always read the question carefully. This said equation of the tangent line and the normal line, right? So this is the tan line right here, tangent line. And the normal line is the line that's perpendicular, right angles to this line. So the normal line slope, I'll write it like this, m normal will be the negative reciprocal of m tangent, right? So the reciprocal means you flip it 2/3 and then the negative sign goes on there. The negative reciprocal of m tan. Okay, so now we're just going to do that to write the normal line equation. I'll write it in green over here. Y minus, we're still at the same point, y1 is equal to negative 2/3 times x minus x1. So this is the normal line. Okay, we can take what we just did further with something called the constant multiplication rule, right? So the constant multiplication rule says that if you have a function f of x, right, and its derivative is f prime of x, then if you multiply this function by 3, you're going to multiply the derivative also by 3. That's basically what the constant multiplication rule says. And the way it applies is when you see f of x equals 3x to the 4th, then we can think f prime is going to be 3 times the derivative of x to the 4th, right? Which means we're going to get 12x cubed. So in practice, the way to do this fast is to think that to take f prime here, we take this exponent, multiply it by whatever's out front. So 4 times 3 is 12. And then you reduce the power by 1. So 12x cubed is my answer for f prime of x. F prime of 1/2 means put 1/2 into the f prime equation. So 12 times 1/2 cubed. 1/2 cubed is 1/8, so it's 12 over 8. And you can simplify that to 3 over 2. Next one right here, f prime is going to be equal to, take this power multiplied by the number here, negative 16, and then reduce the power, x to the 7. So then f prime of 1/2 is equal to negative 16, 1 over 2 to the 7th power. 2 to the 7th power, I believe, is 128. Let me double check. 2, 4, 8, 16, 32, 64, Yeah, 1/28. So I can simplify that to negative 1/8. Next one right here, we have to first think of this as 2t to the negative third, and then s prime of t will be equal to negative 6, negative 3 times 2, t to the negative 3 minus 1, or negative 4. So this can be written as negative 6 over t to the fourth, and if you wanted to do f prime of 1/2, that would be negative 6 over 1/2 to the fourth. 1/2 to the fourth, I believe, is 1 over 16. So now keep the top fraction, change the operator, flip the second, or multiply by the reciprocal to get negative 96. Last one here, 1/3 x to the 2/3. 2/3 is going to multiply the 1/3 to give you 2/9. So for h prime of x, we say 2/9, and then x, again, 2/3 minus 1. Don't let the fractions get you. That's equal to negative 1/3. And this is the same as 2 over 9 x to the 1/3. Also recognize that that's the same as saying 2 over 9 cube roots of x. And then f prime of 1/2 is going to be equal to, let's see, 2 over 9 cube root of 1/2. I'm just going to leave that like that, but that's a decimal that you can get out of your calculator if you needed to. Oh, no, I guess we could simplify this if we wanted to. We could do 2, 9. No, we couldn't. We're just going to leave it like that. You're going to get the number as a decimal if you need it out of the calculator. Okay, so now we can take polynomials and find their derivatives, because polynomials are nothing other than powers and numbers multiplying the powers, right? So we're ready to differentiate a whole polynomial. And what we're using is, we're saying if you start with f plus g, two functions that are added together, then the derivative is going to be f prime plus g prime. And it also works with the minus. So if you start with f minus g, then the derivative is f prime minus g prime. So that means here polynomials are just sums and differences of functions that we just learned how to differentiate. So if I'm looking for f prime of, let's call this f prime of x. If I'm looking for f prime of x here, then for this first one, I just have to say 8x to the 7th plus 60x to the 4th minus 16x cubed plus 30x squared minus 6. And then the last, this right here, the derivative is 0. So that would be my f prime. If you see something like this, we don't know, first reminder, don't do the derivative. This is not the derivative of the top divided by the derivative of the bottom. It's not going to be that. What we're going to learn something called the quotient rule next class, but for now, we have to change this into a sum and difference of powers. And we can do that by simply realizing that this can be written as x to the 1/2. And then we're basically, you can think of it two ways. You can think we're multiplying the top by x to the negative 1/2. You can do that. Or you can just divide each term by x to the 1/2. So whichever way you do it, that first step would be to rewrite the function and get x to the 3/2 plus 4x to the 1/2, right? So I have here, if I do it this way, it's x squared plus 4x to the 1 plus 3 times x to the negative 1/2. So I'm going to get, foiling. When I foil x squared and x to the negative 1/2, I'm going to combine these exponents to get 3/2. Then I go 1 minus 1/2, and I'm going to get 1/2. And then I get plus 3x to the negative 1/2 as my last term. So we have not taken the derivative yet. We simply rewrote the initial function. Now we're going to take the derivative with the power rule and get 3/2. X to the 3/2 minus 1 is 1/2 plus 4 times 1/2. That's 2x to the 1/2 minus 1 is negative 1/2 plus Negative 1/2 times 3, that's negative 3/2. So just write that in as negative 3/2 x to the negative 1/2 minus 1, which is negative 3/2. So that'll be my answer. And if you wanted to or needed to, you could put that into positive exponents, but we can leave it like that for now. F of x equals pi x plus pi over x. You want to realize that this is the first part we already know how to differentiate. The second, you have to write it as a power, pi x to the negative 1. And now you can differentiate and get pi. And then remember, this is going to multiply the pi. Pi is a constant. It's not a variable. And now we take down the power by 1 to get x to the negative 2. So this one can be written as pi minus pi over x squared. When you see a product, right, do not do this is being called I. So I prime is not equal to the derivative of 1 plus t squared times the derivative of t minus 1. That doesn't work, because for a product, there's something we're going to learn next class to do it that way. For now, you have to make it into a sum and difference. So we go 1t minus 1 plus t cubed minus t squared. Just FOIL it out, and now you have a sum and difference of terms. So we can just do what we were doing before. I prime of t is equal to 1. That's from this 1t. 1t is a line of slope 1, so the derivative is 1. The derivative of negative 1, that's a constant, so that goes away. And then we apply the power rule, 3t squared minus 2t. Last one here, we're going to rewrite. Be careful when you rewrite. This has to be rewritten as a power, a negative power. Be careful because it's 1/4 x to the negative 2. The 4 stays in the denominator. This one is 2/3 x to the negative 5. And so then the derivative is, we're going to bring that negative 2 down, multiply by the 1/4. So we're going to get negative 1/2 x to the negative 2 minus 1, which is negative 3, plus, because this minus is going to come down multiplying that one, so it's going to be plus 5 times 2/3 is 10/3, and then I'm going to get x to the negative 6. If you want to put that in positive exponents, then you can do this. Okay, so we have learned now how to differentiate polynomials, and so I could give you a question like this. Find the points on the graph where f of x equals x to the 4th minus 6x squared plus 4 has a horizontal tangent line. Find the points on the graph of that where the tangent line is horizontal, right? So remember, horizontal means slope 0. Slope is the derivative, so we're looking for a place where f prime is equal to 0. So first we're doing f prime of x, and we would get 4x cubed minus 12x. And then we're setting this equation equal to 0. We're not putting 0 in for x. We're saying f prime is equal to 0 and trying to solve that equation. You can solve that equation by factoring, I think. We just pull out a 4x and then x squared minus 3. So then set each factor equal to 0, 4x equals 0, x equals 0. That's one place where the tangent line would be horizontal. X squared minus 3 equals 0, x squared equals 3, x equals plus or minus rad 3. There are two other places, x equals rad 3 and x equals minus rad 3. So these would be all the places where the tangent line to this particular graph would be equal to 0. The slope of the tangent line would be equal to 0. In other words, it's where this graph, you know, if you plot this graph, it's where the graph's going to hit a maximum or a minimum. That's where the tangent line goes horizontal. Okay, position, velocity, acceleration, same idea, just getting you used to those words. Position, s of t, we've got a polynomial, and you're asked to find the velocity and acceleration. So for the velocity, just take the first derivative. Let me show you a little picture here that I use often. Position, the derivative of position is velocity. The derivative of velocity is acceleration, right? So every time you're going down this ladder, we're taking a derivative, okay? So we're taking a derivative every time, and that gets us to the next function. I call it the SWAJ ladder because one year we were talking about this, and I was telling the students that the derivative of acceleration, for those of you who like physics trivia, is called jerk. I'm not joking. It actually is called jerk. And then the derivative of jerk is called snap, and the derivative of snap is called crackle, and the derivative of crackle is called pop, right? But so we took SVAG, and then we were joking that it sounds like a Swedish word, so we call this the SWAJ ladder. For calc, we never get past these three, right? So just remember that. So velocity, back to the lesson, is equal to the derivative of the position. So I'm given the position, so velocity is just going to be equal to, it's good to write s prime of t. That way the reader knows that you know what you're doing. And then you take the derivative and you go 6t squared minus 10t plus 3. This goes away, right, because 4, the derivative of 4 is 0. Okay. Acceleration, just take the derivative one more time. So a is really equal to v prime of t, which is s double prime of t. And that's 12t minus 10. Find the acceleration at 2 seconds. Well, we just do a of 2. 12 times 2 minus 10. 24 minus 10 is 14. If this is in centimeters and this is in seconds, velocity will be in centimeters per second. Acceleration will be in centimeters per second squared, because it's like centimeters per second, that's already velocity. If you divide that by another time unit, you get centimeters per second squared. Okay, last part of the lesson is about the derivative of the exponential function, right? So exponential function, super important function, it's e to the x. That's the natural exponential, right? So let's talk about what that looks like. If you made a little table, x, e to the x, e to the 0 is 1, e to the 1 is e to the negative 1 is 1 over e is about 2.7, and 1 over e is roughly 0.37, I think, if I remember right. We'll call it 0.4. So if you made a graph of this, then 0, 1 is on the graph, 1 comma e is on the graph, right? So about 1 comma 2.7, that's on the graph. And then this point is at negative 1. And then 1 over e, we're saying it's roughly 0.4, something like that. We know that this graph has a horizontal asymptote at x is equal to, y is equal to 0, right? So this line right here is my horizontal asymptote, the x-axis. So that's just a quick review of e to the x. The reason e to the x is very special, well, there are so many reasons, but one of the reasons is that the derivative of e to the x, and I'm going to write it like this with the Leibniz notation, d dx of e to the x is equal to e to the x. That means that the exponential function is its own derivative. So if you come to a point like right here on the exponential function at this point 1e, and you drew the tangent line and you asked what is the slope of that tangent line, it would be equal to this exact same value, right? So the f prime graph and the f graph look exactly the same for the exponential function. And so when we talk about a function which is like this, first let me just say if f of x is equal to e to the x, then f prime of x is equal to e to the x. The exponential function is its own derivative. So if you're looking at something which is an exponential and a polynomial mixed together, we can now just say, it's a sum and difference. So I can do f prime of x equals e to the x minus 1. This is still the line y is equal to minus x. Its derivative is minus 1. This is two functions that are being subtracted, right? So I can take the derivatives separately and just put them together like that. F double prime of x, well, it's e to the x, and then this goes away because the derivative of the minus 1 is 0. Find a point on f of x equals e to the x such that the slope of the tangent line is parallel to y is equal to 2 x, right? So we're saying we want to be on this graph, e to the x, and then if I drew the line y is equal to 2x, which looks something like this, right? This is y is equal to 2x. We're saying where on this exponential graph would I have a tangent line, right, that's parallel? It looks like be somewhere, oh, maybe not. Let me see. I feel like it would be somewhere here, maybe. Let's see. So how do we solve that problem? Well, we know that f prime, the slope of the tangent line, is e to the x, same thing as the function. And so the slope here is 2. So then when e to the x is equal to 2, that must be the place where my tangent line would be parallel to this y equals 2x line. So solve this by taking an ln. X is equal to ln 2 would be the place, and ln 2 on a calculator is 0.6931. So yeah, I mean, not bad. I feel like, if this is 1, I'm not far off from 0.6 for a very rough graph here. So, right, anyway, this is how we do the problem right here. Okay, last problem, or takeaways. So pause the video, see if you can differentiate this first one, and then see if you can write the equation of the tangent line to this f at the point x is equal to 0. Okay, so the derivative is just the power rule, so 2x, and then here minus times a plus, this is like a plus 1, so you get minus 2x to the minus 3 plus 1/2 x to the 1/2 minus 1, right, which is negative a half. E to the x, the derivative is just e to the x. 2x, the derivative is 2, and the number goes away, no derivative, right? So that's my derivative equation. Tangent line equation, well, I'm at the point x equals 0, so the point, I need a slope. The point is 0, and then to get the y value, we're putting this 0 into f of x, into the function, right? Not into f prime. So put it into the function, and I think you're going to get, let me erase my work here so you can see the function again. Okay, so I'd get 0 squared plus 0 to the negative 2. I'm just writing this out so you see which ones go away and which ones don't. 0 to the half, e to the 0, 2 times 0 plus 1, right? So these guys go away. 0 squared, 0 to the negative 2, 0 to the half, 2 times 0. All that just goes away. And then e to the 0 is 1. 1 plus 1 is 2. So my y value is 2. And for f prime of 0, that's the slope, right? The slope is f prime. I come to this equation right here that I found, and I put in 0. So I get f prime of 0 would be 2 to the 0. That's 0 minus 2 to the 0 to the negative third. That's also 0. Any power of 0 is 0. And then 1/2, 0 to the negative 1/2. That's 0 plus e to the 0 plus 2. So all these are just 0, and then e to the 0 is 1, and plus 2 is 3. And so my slope at this particular x value is 3. So then my equation for the tangent line y minus 2 is equal to 3 times the quantity x minus 0. You can rearrange that, but you don't have to unless the question asks you to. So there you have it, derivatives of polynomials and exponentials. Practice makes perfect. Please make sure that you understand and do the homework really well, and keep on practicing your derivatives, and I will talk to you next time.